Thank you so much. It's a pleasure to be here to present our developments on the high throughput screening microscopy. Actually, we are developing multisensorial hyperspectral and multimodal microscopes for identifying massive population of targets in microscopy. I'd like to, for those that are not familiar with the field of the high content or high throughput screening microscopy, this technology has played a very significant role over the years on molecular biology specifically, and it includes in a single platform imaging modalities, robotics, image acquisition, data handling, and so on, and has revolutionized several fields in molecular biology and towards developing new drugs and new diagnostic and treatment methods. In fact, this system is being able to automatically scan all kinds of molecular population or cellular populations, primarily being tagged with fluorophores. Sometimes they are using multiple fluorophores, and this way they, at the end of the analysis and the acquisition, there is a multi-step pipeline that includes the analysis of this massive amount of population of the data, and at the end of the day, it comes up with enumeration of the cells which are positive or negative, etc. And it has played, as I said, a significant role all this period of time. However, the main issue of this technology is that it primarily works with fluorescence sensors. So it has one sensor that captures fluorescence for 2 or 3 fluorophores, and these systems are not intended to provide real-time composition analysis in microscopic samples. It's just to identify fluorescent positive or negative biological specimens, to enumerate them and to classify in different categories. So we have capitalized over this, we try to capitalize over this significant technology because the way it works today, the analysis, I'll start from the field called forensics imaging. What they do, they actually collect traces from the crime fields, and the task is then to analyze which are these traces, whether it is semen or blood or DNA material or a variety of different kinds that can be found, either are human or natural materials. So the idea is it possible to scan a full region of a crime field and then put them on the microscope and do an analysis that runs in a completely unsupervised manner, and that after 3 or 4 hours to give you results about the chemical identity of the traces and to be able to classify whether there are existing some materials. Not only in forensics, though, there are many applications, industrial or scientific, that people want to do the analysis in an automated manner in microscopy to figure out where there are features of diagnostic importance and so on and so forth. So in order for a high content screening microscope to be able, within like a few seconds per field of view, to analyze and to identify the features that are seen under a microscopy objective, the way it works today is they're using several complementary techniques, including fluorescent microscopy, FTIR, Raman, spectroscopy, polarized microscopy, hyperspectral microscopy. And so there are many different devices, different sensors, that there are several problems in comparing results from the different sensors, and it is very time-consuming task, actually, in being able to pass a sample through all this pipeline of microscopes and spectroscopic techniques. And that is the problem that we want to address with a multisensorial high-content screening microscope that we have developed. And in fact, what we do, we have the ability we want to identify even traces or features that are transparent. There are many of those, like collagen, for example. Collagen is transparent, it's scattered, or some other traces in forensics are transparent. In this particular case, we emphasize in measuring and mapping anisotropy properties of the material, and particularly we talk about birefringence. Second, we want to identify the spectral characteristics of the materials which are related with electronic structure and other structures of the specimen. So the multi-source-area aspect of our system is that it can do snapshot real-time hyperspectral imaging with the devices that we have developed and represented in Outstand. We do multi-wavelength fluorescence excitation using multiple lasers for fluorescence excitation and multiple wavelengths for the imaging. And we also use polarizing microscopy, but the particular contribution is that we have developed a method to measure the birefringence in any pixel of the specimen. Birefringence measures actually is a measure of the some materials that are presenting optical anisotropy. They have two indexes of refraction, and this is, if you measure the difference of these two indexes of refraction, you have an index that can characterize a material based on the birefringence properties. And at the end of this acquisition process, we collect like 19 images from the hyperspectral, 9 images from the fluorescence, and 12 images from the polarization, which are modeled with Stokes polarimetry. And so we end up with a data set which is, includes all these images. And this is the block diagram of our system that has all the transmission, reflection, and polarization optics. This is the acquisition. So we acquire all these 40 images within 3 seconds. And then there's a training process with golden standard material to make chemical identity maps using machine learning technology. So this is how the system looks like. It has a large surface over which the user can dispose all kinds of samples, either there are industrial samples or there are biological samples or forensic samples. And then you leave the system to work without supervision. So what it does, it goes in its particular field of view and captures all these 40 images, fluorescence, hyperspectral, and birefringence. And so all these images provide complementary information for, it's very unusual for a material having, different materials have exactly the same characteristics in all these imaging modalities, which give us, as I said, complementary information. And at the end, we are generating a training data set where with ground truth material, these feature maps are correlated to particular chemical identity maps. This is an example. I'm going to end my presentation with 2 examples, one from forensics and one from histology. So this is from forensics. They are using tapes to collect the traces in the crime fields. And if you ask the forensics department to analyze, identify all these tapes, it will take like 2,000 years for them to analyze frame by frame. It's impossible. And that's why what they do sampling. So they select 2 or 3 sites that they, with the naked eye, select as the most probable to find some traces. And they do this analysis this way. So it's selective and subjective. So the new guidelines is that you need to tape all the crime field. And then there is a massive amount of background material which are not important, like soil from the ground, but also there are trace evidence materials that are very useful. So we have developed the system, as I said, and we have ranked it first in a European tender, and we have installed this system in the NFI in Netherlands, in the National Forensic Institute. We have installed this in the United Kingdom, in the DASA Center of the Defense Minister of UK, and also in Lithuania and other countries. And we have, as I said, many installations, and we received some Best Paper awards for this work. And the end point is actually, you see how an image looks, and this it's an original tape which includes hairs and all kinds of of traces, it's impossible to enumerate them. But here, in a completely unsupervised manner, it not only identifies here or fibers or things like that, but also enumerates them, which is very important to figure out what is the privilege. So the high content screening capacity here is actually demonstrated in this slide. We capture about, as an example, to give you an idea, is like 3,000 fields of view with an objective of ×5 or ×10. You generate 144 images with 3 or 5 seconds per field of view, that means that the acquisition time is 5 hours and the analysis time after the training is also 5 times, because 5 hours is very fast. If you do this same field analysis with like 1/3 of the techniques that the system integrates, it takes 37.5 days. So it's not possible to do this. So we improve the workflow by a factor of 180%. So that is for forensics, and this is becoming a standard now in forensics labs across Europe. And now that's another application where we exploit the birefringence aspect that we have developed. So what's the problem? I don't know if I'm sure very few people are familiar with amyloidosis. Amyloidosis is a very important disease which leads to dysfunction of several organs and also the failure of several organs like cardiac tissue. And today, the way that they diagnose amyloidosis is using a stain which is named as Cogored, and they use polarized microscopy. But if you have, and what they try to do, Cogored aligns with the fibers of collagen, and they change the birefringence of the material, so it's very characteristic. They give you some colors, interference colors, on polarization microscopy. The problem is, though, that these colors are very subjective, the estimation, and because the optical axis of these fibers can be in a random positioning, these colors change also because of the random positioning of the optical axis of the birefringence material. So that's a problem in finding a way to diagnose whether this is amyloidosis is positive or negative, and there is a fight internationally. When they see red colors is positive or green colors are positive, it's still ongoing, this fight in the histology journals. So we developed, our method is completely orientation independent and intent up to this is maps where, as you see, this is the regular polarization image. There's not much information on the concentration of the amyloids, the amyloidosis, and then in this image, which you have a map of the birefringence, you see exactly the location and the problem related to the dysfunction of the conformation changes in collagen structure that it's induced because of amyloidosis. So what we're now going to do is that we introduce a new diagnostic index for histology, and this index will be birefringence, which is a physical property. And this will be completely independent now from subjective estimations, and we hope that this way the impact will be huge, because amyloidosis affects hundreds of organs, and there is no trustable diagnostic process as of today. Coming up to the conclusions is that we have developed a multisensorial, multimodal, high-content screening microscope for quickening and automating the analysis in a variety of fields. We have a new method and technology to analyze in real-time optical anisotropy and integrate to the same system. We have a new technology for identifying and triaging in forensic traces, which is completely unsupervised and objective. And this is a ready product. We have already installations, but at the same time, it comprises a valuable platform, research platform for pharma industry and other industries, like anywhere you will need seed sorting, pharmaceutical products, molecular biology, film, polymer, etc. Thank you so much for your kind attention, and I'm happy to. I'm within the time, right?
Yes, exactly.
Excellent.
Thank you very much for this interesting talk. Are there any questions?
Hello everyone, thank you for being here. So I'm a PhD student and this is my topic. So how to merge computer vision and robotics improve visual inspection planning. The reason why we are interested in this topic is related to sustainable manufacturing. So industry, as you know, they want to have products with really high quality. They want to produce components with really complex geometry, and of course, they would like to increase the outcome. At the same time, they would like to reduce the cost, reduce the waste, and reduce the production time. We are mostly thinking about die casting applications. So there are two main reasons. One is that there are huge incomes from automotive in this sector. And the other main reason is that there are really high dimensional accuracy, smoothness, and high productivity requirements. Here you can observe some defects that usually occurs on this type of objects. We have, for example, some cracks, blister, and so on. And these defects can be categorized in different ways. In my PhD, I'm mostly interested in geometry, so in those defects that we can observe from outside. Right now, the standard in visual inspection planning is based on the human, so usually it's not a inline inspection. Every component is removed from the production line and is manually inspected. This, of course, is time intensive, and there is also another problem that is related to the performance, as the performance of the inspection strictly depends on the employee expertise. For this reason, we are thinking about developing a different solution that takes into account robotics. So we would like to develop an automated visually quality inspection system. There are some requirements to do so. We need a robotic solution, an inline inspection, and high speed and high accuracy. A robotic solution is needed to improve the flexibility and reduce the human errors. The inline inspection is needed to keep the production time low. And when I'm talking about high speed and high accuracy, I'm meaning 30 seconds per part with an average accuracy of 0.3 millimeters. So our idea is to develop a system like this. We have some external specification from our customers, for example, where to inspect and how to inspect. Then there is the inspection, pose, and motion planning. That is the part in which I'm mostly focusing during my PhD. So how should we inspect the part in order to be really fast and cover all the surface? This is done on offline. Then there is an inline part, that is the part in which we actually gather the data. And finally, there is the quality control step, in which we do something with this data, like we reconstruct the model or we derive other metrics. The visual inspection planning can be formalized as coverage path planning. So as I said, there are some external specifications. For example, the 3D model of the object that we want to inspect and the model of the sensor that we want to use. Then we generate some inspection poses, and then we derive a collision-free path in order to be able to inspect the part from all these parts. In this way, we are able to obtain an inspection plan. There are two main approaches in the state of the art. One that is computer vision based, and in this case, optimal inspection poses are generated based on the object, so based on the geometry of the object. And another approach that is robotics based, and in this case, the inspection poses are generated sampling the workspace of the kinematic setup. However, both methodologies have some limitations. In case of the computer vision method, the inspection poses are optimal for the object, but given a specific kinematic setup, may be unfeasible. This means that the robot will not be able to place the end effector in correspondence of that pose. And in the case of the robotics method, of course, the inspection poses are feasible, as we computed them sampling the workspace of the kinematic setup, but some portion of the object may be uncovered. For this reason, we wanted to develop a new method that takes into account both computer vision and robotics. So first of all, we generate seed inspection poses based on the geometry of the object, and then we refine them, taking into account the kinematic setup. To do so, first of all, we need a method to generate these seed inspection poses. Then we need a metric to evaluate the coverage, so to know how well we can see with these inspection poses. And finally, we need a method to refine those unfeasible inspection poses. Here you can see the flowchart of the pipeline I developed. First of all, we generate these seed inspection poses based on the model of the object and of the sensor. Then we evaluate this feasibility and visibility evaluation, and we correct those viewpoints that are unfeasible. And finally, we solve the set coverage problem, that is an integer linear programming problem that provides us the smallest number of inspection poses to obtain all the data that we need. So there are in literature many methodologies actually to compute these viewpoints. What we did was to develop a new method that we call surface method. And the reason is that our method depends on the shape of the object, while some of the methods in the state of the art, they don't. There is a lower computational cost. It has just 2 parameters to tune, and is actually pretty intuitive to implement. What we do is that we have the 3D mesh. We apply Poisson desampling, so we have some sample on the object, and these samples are spaced from each other of a specific radius. And once we have them, we apply a standoff correction. This means that we move along the normal of this sample of a distance equal to the working distance of the sensor. In this way, we are sure to have our object in focus. And finally, if there are some occlusions between the line of sight of the sensor with the sample that generated it, then we correct them. And in this way, we have our inspection pose candidates. We compare our method with other methods of the state of the art on three different objects that actually were already evaluated in the state of the art. And we found out that surface sampling methods, and in particular Poisson disk sampling, is the one able to achieve full coverage with a number of optimal inspection poses or viewpoints that is lower or comparable to the other methods. So at this point, we have some inspection poses, and we need to evaluate them. So usually the evaluation is done via ray tracing. This means that some rays are traced from the focal point of the camera through the scene. And based on what each ray hits, we are able to understand what we will see from that specific inspection pose. And these information are stored in a matrix that is called visibility matrix. This matrix is defined as 1 if a surface element can be seen from a specific viewpoint, or 0 otherwise. So for example, in this slide, you can see that Vij is equal 1 because the viewpoint I is covering the surface Si, but Vi plus 1j is equal 0 because in that case, that surface element is not covered. This definition presents, however, some limitations because when we are in this situation, you can see that we have one inspection pose, and you can see that there is just one ray that partially hit a face. So with the standard definition, we would just that the face Si is visible. But actually, I would say that this is not well seen. There is a big portion of the face that is not covered. So what we did is that we started from the concept of spatial resolution that relates the area of the image sensor with the number of pixels, and we derive the surface element density. So in this case, we don't use the number of pixels, but the number of rays hitting a surface element, and we don't use the area of the image sensor, but we use the area of the surface element that we hit. So when we are in the situation like the one on the left, in which you see that there are two inspection poses, in which one inspection pose is covering for real the object with the surface element density that we want, then we use not 1 or 0, but a normalized value. So the normalized surface element sampling density. When this is not the case, like on the right, then in that case we use the standard visibility matrix because we prefer to cover one face with at least one ray than not see it at all. Once we have this matrix, then we solve the set coverage problem. And here you can see that when we use the standard visibility matrix, we have many areas that are in blue there, while when we use our sampling density matrix, we have many areas in red, where red means higher density, so more points in our point cloud. And this is actually what we want. And also, if you look on the plot on the right, when we use the sampling density, we are on the left of the target spatial resolution. That means we are able to obtain a spatial resolution smaller than what we wanted, and this is good. When we use the visibility matrix, then we have some surface elements that are covered with a worse resolution. So at this point, we have some inspection pose candidates. We have a way to evaluate them, but actually it can be the case that some inspection poses that we design are not feasible, because the feasibility depends on the kinematic setup that we want to use. And for example, if you have a setup like this one in the picture, you have just 3 degrees of freedom. You have a linear axis, a turntable, and a goniometer. Maybe you want to use such a setup because it's cheaper, or maybe because you can have higher precision with respect to a robot. So we need a way to correct, to improve those unfeasible inspection poses. And what we did is that we developed an optimization pipeline based on Bayesian optimization, in which we start with an unfeasible inspection pose. First, we apply an orthogonal projection so that we are sure to have some initial valid solution. And at that point, we start an optimization routine in which, first of all, we try to find a new feasible inspection pose that provide the same coverage, so that is covering those faces that were covered from the unfeasible inspection pose. Then we would like actually to find a feasible pose that can see what was previously covered, but even something more, if it's possible. And finally, there is a third term that aims to cover those phases that are actually not covered already from other feasible viewpoints. In order to validate our method, we compare it with other 2 methods. In case of workspace sampling, what we did was to sample the workspace of the robot. So in that case, we are sure to have feasible inspection poses that actually are not optimal for the object. And in case of the box constraint, we apply just an orthogonal projection from the unfeasible space to the feasible space without adding any optimization procedure. And we evaluate these 3 methods on different objects, like rabbit that is more convex and concave, this bracket that has some holes, a parallelepiped that is sharp, and finally a gear and a hair that have some self-occlusions. Here you can see some results. So actually our method that is indicated as BO is the one that is able to achieve highest coverage with a number of optimal inspection poses that is lower or comparable to the other methods. We also validate our method with real experiment. So here we have the setup that I was showing before. We have a single stage axe, a turntable, a goniometer, and a 3D printed plastic rabbit. And we use structure light sensor. In this case, it was Zivit. We also had a digital twin in which we were able to evaluate how the object was going to move. And the object moves on the setup so that the camera can acquire point clouds from different views. And then these views are stitched together, for example, with global ICP or generalized ICP in order, for example, to reconstruct a 3D model. Here you can see some point clouds that we obtained from the different objects. And what we did was also to compare the 3D printed plastic bracket with a die-casted one. The idea was to evaluate how different surfaces impact on the same geometry, and we were able to inspect both objects and cover them fully. So this was our pipeline. Some remarks. We needed a method to generate seed inspection poses, and we did it with this Poisson desampling method. Then we needed a metric to evaluate how good these seeds are, and we defined a new metrics based on the spatial resolution. And finally, we needed a method to improve those viewpoints that were unfeasible. So in the future, we would like to implement this solution for redundant robots. We actually have, we are already actually able to implement it with a normal robot, like 6 degrees of freedom. It already works, but we would like to have, for example, 8 degrees of freedom or more. Of course, we want to keep experimenting on objects with different geometries and different material surfaces. And finally, we would like to improve speed, coverage, and accuracy. Thank you. If you have questions, I'm happy to reply.
Thank you very much.
Welcome. Hello, everybody. My name is Nadim Amari. Thank you for the introduction. So just a little bit glance. We are similar to the Austrian Institute of Technology, but we are the Swiss Institute of Technology. We are located at different locations across Switzerland. Our objective is to exactly what you do at AIT, is to transfer technology from academia onto the industry. We mainly focus on 2 pillars. One is applied research, and the second topic is about tech transfer. We have lots of, coming from the Swiss industry, we are working a lot with the watch industry. We have expertise in ultra-low power operating system, photovoltaic cells. We have embedded AI in multiple applications. We are known for miniaturized atomic clocks and also for automated machine for personalized skin re-engineering. Our main focus at CSM are threefolds. One is digital technology, precision manufacturing, and sustainable technology. I am mainly focused on the upper corner of the digital technology, where we are working on ASIC for the edge, data and AI, and vision and IoT. My talk today is all about metrology through imaging. Today, we know on the state of the art, we have 3 scenarios in which we are doing metrology on a machine. The first one is either through optical encoder. We have big names like Heidenhain. We also have interferometry, which is quite used also in metrology solution. And the last, let's say, state-of-the-art and most relevant topics is capacitive or inductive sensing. And these are really dedicated for proximity short stroke actuators. The main dilemma about these types of technologies is twofold. One, it's a type of point measurement, so you don't have an image which is being formed. And the second aspect, it is a single degrees of freedom measurement that is being done. We are not able today, with any of these technology, measure multiple degrees of freedom at the same time. Okay? So this is where we come in with a novel type of technology which is based on shadow imaging. The principle is quite simple. I need the laser pointer for a second. Okay, so we have 3 components. The first component is LED source, which any type of illumination which is taking place. The second component is a mask, which is being done by simple lithography or any type of grating mask that is possible. And the third aspect is an imager. Okay? And here the main point is that we are constructing the full image, the full shadow image. On the left is a simplified representation, okay? And on the right is a typical implementation where we have an imager, a pattern grating, and on that pattern grating we have fiducials to ensure the repeated phases are in line, and the third aspect is a light source. Okay? To give you the idea of how the added value of this type of metrology system, if you compare it to a standard approach where you have a single LED, an optics and a sensor, the spot size that you end up on the detector is a few pixel size width. Okay, and the resolution that you end up with is the order of magnitude of the pixel pitch that you have. We could interpolate, but we end up with something in the range. On the typical imager, I have a pixel pitch of 5 microns. We end up with a precision limitation of 5 microns. Now, in contrast, if we looked at the space coder approach, which is based on shadow imaging, here we are using the full detector for our system, and we have the full projection of the shadow mask on the sensor. And this allows us, one, to be able to average all the errors that we have on that system, and we are able to reach sub-pixel resolution up to 10 nanometer. The 10 nanometer here is actually the intrinsic limitation of any type of detector, any type of commercially or industrial detector. Based on the electronic shot noise that we end up with, we are not able to go beyond 10 nanometer. When we talk about the imaging, the processing pipeline, it is quite simple. We have the light incident on an encoder disk or a diffraction grating. Okay, we capture the intensity of the pixel, then we sum along the rows and we sum along the columns. Once we have that, we convolve it into a sine, cosine, and based on the angles between that we are able to get, we are able to get the phase measurement of the shadow image that we are getting, and getting the position of the LED source relative to the detector itself. In terms of stability for the system, we measured along different type of stability solution, and we have recorded measurement of 48 hours, which is approximately 3 million measurements. Okay, we had in a fixed environment, dark condition, on the stable condition, and we are able to get a standard deviation of 10 nanometer and a peak-to-peak variation of 80 nanometer. This is along all degrees of freedom, so X, Y, Z, and also along the posture. Okay, we are able to decrease it a bit more by removing the long-term repeatability due to the thermal drift by going something in the range of 15 nanometers when we consider two measurements which are 2 hours apart. So here the main point that I'm explaining, that the simplicity of an LED, a shadow mask, and an imager is able to get nanometer level precision. Based on that, we did multiple technology transfer. One is used in the hexagon touch probe, in which the full system by itself is able to reach something in the range of 300 nanometer. But the most interesting part is the triggering, which is limited to 5 microseconds. So we have 5 microseconds in which we are doing the exposure, we are doing the processing, and we are sending the information of the relative position of the touch probe during operation. This is very important, specifically when we are touching a contact surface, and we want to be sure that the contact point is accurately sampled. Okay, all in all, the full system is, including the mechanical assembly, we are at 300 nanometer. And for that system to be able to reach the 5 microsecond cycle time, we had to develop a dedicated ASIC. The dedicated ASIC for it, which is embedding both the imager and the processing required for it. Another application showing a different axis of the technology is used in the medical for knee replacement, and this is showing the dexterity of the technology that we are offering. So here we are by no means in the range of nanometer, we are in the hundreds of microns, but mainly because we have a field of view of approximately 90 degrees and a temperature range from 10 to 30 degrees. The layout is still the same. We still always have an LED sensor, okay? And on top we have a mask, a lithography mask, and an imager. This is already transferred to one company, Medivation, which they are already implementing in lots of applications. Now, Having said all of that, everything is nice and clear, but we have an intrinsic limitation inside the space coder technology inside of shadow imaging. So if I take the intrinsic limitation of a sensor, which is approximately 10 nanometer, considering shot noise, electronic noise, and so forth, okay? And my shadow mask is located at a distance d1 from my sensor. I cannot be completely, I cannot glue my shadow mask directly on the sensor because I don't have any shadow anymore, so I need a certain distance. And the object which I am trying to measure is, for example, at 1 meter away. Okay? The main problem is that I have an amplification of my sensor noise from the sensor plane onto the object plane. Meaning that if I have 10 nanometer at my sensor level, I'm going to end up with 10 micron error I'm getting at 1 meter away. Okay? The main point, the main approach in which we are able to overcome this limitation is by increasing the distance d1 between the shadow mask and the sensor. The problem with that is that we end up with diffraction and we lose on the resolution, because now the grating that we are getting on the sensor are no longer consistent with the shadow mask. Okay? So we have these two limitations that we are not able to overcome. And this is what the novelty of our technology is, the possibility that we leverage the Talbot effect. So the Talbot effect is quite simple, in which if you have a plane which is a plane wave incident on a repeated pattern, the diffraction will be periodic, okay, until we reach the point of the sensor. And for that, this allows me to increase my distance to the shadow mask, increase the distance between my sensor and my shadow mask. Meaning now the error that I'm getting on my sensor, which is stuck at 10 nanometer, I'm able to decrease it onto the object plane. Okay? And here on the left is the diffraction pattern for the Talbot effect. To better visualize it, I did a small animation. I try to see if it works. Yeah. On the bottom you see the actual images that we are getting on the imager, and on the right is an animation in which we are seeing how the mask is moving. Let me repeat it one more time so you can see it a bit better. Okay, so we see that somewhere along the line we are losing focus, then we are capturing focus. So we could be multiple Talbot distances, put the multiple Talbot distances between the mask and the image. This is what we refer to as the Talbot carpet. And with this type of system, I'm able to reduce the projected error from the sensor, which is order of magnitude of 10 nanometer for a 5 micron pixel, to something which is sub-nanometer, as you're going to see in the next slide. This is the experimental layout that we put in our lab, and here I have with me, if I'm able to find, yeah, thank you. No, I just need this one. Yeah, and I have with me the same experimental setup that we built for a demonstrator, which at the end I'm willing to show it to you guys. Okay, and here what we are doing, this is the laser. This is the mask, which is extremely close to the laser, and the imager is several Talbot away from the imager itself. Okay, and we are measuring. We're doing a step for the imager of approximately 10 micron, and we are capturing this with 650 increments. So meaning phasing, we are getting 650 increment, and this leads us to a resolution of approximately 0.5 nanometer 1 sigma. Okay, and here we are measuring in 2 degrees of freedom. In 3 degrees of freedom. I'm measuring the XY plane, so everything which is perpendicular to the scanning, to the optical axis, and also the Z axis, I'm also measuring it. So in summary, we developed a metrology system which is based on shadow imaging that leads to a 10 nanometer resolution on the sensor plane. The simplicity of the processing pipeline that we have, we are able to push with a dedicated ASIC something between the 40 to 60 kilohertz in terms of processing time, and we are able, because it's an image-based system, we are able to get 6 degrees of freedom from a single point. Okay, of course it's a lensless solution, so we cannot refocus any of the optical rays. So we have the issue of the diffraction, which is due to the distance between the mask and the imager, and this is where we introduce the Talbot induced diffraction. So this is, for once, physics working on our side, and in which we are able to increase the distance between the mask and the imager, and decrease the resolution that we are able to get on the object level to something of the order of 0.5 nanometer. Okay? This is it from my side. I'll take the opportunity to say that CSM is now having the 40th anniversary by the end of the year. Thank you very much.
Thank you very much.
Okay, thank you for introduction. Hello everyone. I'm Hong-Suk Lee from Miracle, and today I'm going to talk about how to maximize your inspection accuracy with deep learning. So I have like the 4 parts. Firstly, I'm going to talk about like synthetic defect data, and secondly, I'm going to talk about anomaly models. Third, our unique models, which is a patch classification, and lastly, I'm going to talk about like auto deep learning algorithm. So before we start, let me give you one question. Like, what do you think of the end of goal of the deep learning vision inspection? We have to think about why we are using deep learning. It's very simple, actually. Why we are using deep learning? Because we want to maximize the deep learning inspection accuracy. If we can maximize the accuracy with the conventional one, we are going to go for it. But there are so many irregular defects, so that's why we are applying deep learning to maximize the accuracy. However, try to maximize the accuracy. There are some challenges we confront. Maybe we can categorize in 3 things. The first one is data scarcity. So you know, normally we can easily gather OK data from the manufacturing lines, but it's very difficult to gather some defect data. So we have to solve this problem when we're applying deep learning, because deep learning is basically learning-based algorithm. And secondly, there are some data imbalance of each classes. Because, for example, you have like 5 different types of a defect, maybe 1 or 2 types of defect you can easily gather, but others, it rarely happen. In that case, we also think about how to solve these problems. And lastly, nowadays, we try to have very new application with high-resolution images. In that case, we have to think about how to minimize how can I say, missing information in this high-resolution data. That's because deep learning, when we train the model, we cannot use so big image data. Sometimes we have to resize, sometimes we make patches, but we have to think about how to solve this problem. So for that, I'm going to introduce 3 things. Try to solve the data scarcity. I'm going to introduce synthetic data methodologies. Secondly, I'll try to make some data imbalance better. I'm going to introduce anomaly models. And lastly, try to deal with high-resolution data. I'm going to introduce patch classification model. Let's go to the first topic, synthetic data, to solve the data scarcity problems. So as I mentioned, in the manufacturing side, we are lacking of the defect data. So this is a big problem. So try to solve this problem. We introduced the GAN model, Generative Adversarial Network. So in GAN model, actually, we have two models. One is the generator, and the other is the discriminator. So generators will create new images. Actually, here, we compare with some like the police and some, how can I say, counterfeit money criminals. But generators will generate the new data, and the discriminator will discriminate whether this is the real or whether this is a fake. So compared with these 2 networks, the GAN model can create a very accurate, very suitable image data based on your defect types. So this is how you use a GAN. Of course, we have to teach the defect types, defect shapes, so that we need at least 10 defect data, and then teach training the GAN model. And then after you train the GAN model, you're going to use the OK data. And then based on the OK data, you're going to put these defect stamps on the surfaces. And then GAN model will generate artificial defects, synthetic data like this. This is the basic concept of the generative adversarial network. And of course, GAN model, we have 2 networks inside, as I mentioned, discriminator and generator, so that a GAN model is actually a little bit a heavier model compared to the other normal models, because it includes 2 models at the same time. So that means actually it's also difficult to handle high resolution data. So we have a patch mode of a GAN model, to train and to create the very small defects on the high resolution images. And also, as I mentioned, we only need 10 defect data for the training, so it's very practical to use on the manufacturing side. And also, we provide the stamps, defect stamps, when you create new artificial defects based on the OK data, because we train like the 10 defect data, but when you generate the images, if you put some really bit strange labels on the OK data, then maybe your GAN model's performance can decrease. So that's why we provide defect stamp pool to make the multiple synthetic data very well. Yeah, so you're gonna put these stamps on the OK data, and you can easily create. So we have many use cases. For example, like this is an example of the inspecting batteries. So batteries, sometimes it's difficult to gather some defect data, so that's why we use GAN. So before we use GAN, the accuracy is around like 87%. But by using GAN model, we generate like 40 defects about the foreign substance and 80 defects of the dent images. And then the accuracy goes up to around like 97%, which is higher, 11% higher than a previous result. So this is one of the advantage of the GAN model when you're having a hard time gathering some defect data. Let me go to the second topic, which is anomaly models. If you have some class imbalance among your defect types, this is also a problem. As I mentioned, maybe defect 1 and defect 2 you can easily gather. You have maybe like the several hundreds of the defects for the first and second defects. But maybe for the defect 3 and defect 4, you only have 1 image or 2 images. If you train these trained data, then there's a high possibility that the model can detect only defect 1 and defect 2, and it cannot detect defect 3 and defect 4 because of this class imbalance. In that case, we recommend to use these anomaly models, because nowadays we have to detect this irregular defect type. That means defect types is getting number of the defect types is getting larger and larger. So that's why we are thinking of using this unsupervised learning, which we can call the anomaly models, because in this case we only train the normal data. We only train the normal data. That means the models will learn what the boundary of the normal data is, and then we can easily find out abnormal cases without any big amount of the each defect types. Yeah, so we provide 2 types of different anomaly models. One is anomaly classification, and the other is anomaly segmentation. The result is very similar like the normal classification and normal segmentation. So classification, as you can see, we provide a heat map, and then for anomaly segmentation, we provide some blobs on the surfaces. So as I mentioned, the biggest benefit of this anomaly model is we can train when the defect data is very insufficient. And also, we can minimize the resources for the model training and model image labeling. Normally, we only train the normal data. That means actually training process is much simpler than the normal training, so that we can minimize the training time. And as well as, we don't use the defect data for training. That means you don't have to label one by one for the defects. So this is another benefit of the anomaly models. So there are also many use cases, but one use case is finding some missing pallet on the logistics. So in that case, 5 pallets should be placed in each sections, but normally it does. But sometimes actually there are only 4 pallets. In that case, we can use this anomaly to find out some missing pallets. So yeah, because in this time, it's really difficult to find some defect data, so that's why the accuracy of the normal classification was really low. But anomaly can solve these problems. Yeah, I'm out of time, so I should go faster. So maybe the next one is the patch classification to overcome the limitation of the previous classification model. And as I mentioned, these days, we are using very high resolution data. For example, we use many line scan camera. In that case, the resolution is really, really big. But the problem is computation power is not that big. We normally, when you're using classification model, maybe we have to resize the data into 1024 by 1024 or 2048 by 2048. But that means if your original data is larger than like the 10K, that means you have to resize at least like 5 times or 10 times. But if the defect is large enough, that's okay. But if the defect is very small in this high resolution data, then it may cause some problems. That means the models cannot detect those defects. So we want to solve this problem. So maybe we can think of, okay, I have a classification model. Maybe I can just divide the original images into these kind of like the patches. It works. Sometimes it works, but if the defects are large enough, then actually defects will be divided into different patches. That means if you just divide these patches, actually you cannot meet your highest accuracy because there will be some missing information between the borderlines. So that's why we invented this patch classification. Of course, we divide patch by patch, but of course there's some algorithm. We make a balance between all the borderlines. So you don't have to worry about any information missing between the borderlines. You can just draw the labelings like this with the patches. Then our patch classification model will train it and then find out the defects on the high resolution data. The first one, you can click it for labeling. You can drag, or you can also make a batch labeling for each patches. This is what we provide for labeling for patch classification. So another benefit of the patch classification is very easy to integrate, because if you just divide the patches by yourself, you have to think about the pre-processing and post-processing of the classification model, and it takes some time, and then sometimes it makes some error because it's not easy. But we have our total pure model of the patch classification. That means you can just import your images into our model. Then our model will predict. Our model will make all the patches into the original data, then get the result. So it's also very easy to integrate into your system. So we have many cases of this patch classification, and one use case is the wire defects. In this case, we have to detect very small wire defects, so that we are using line scan camera to get some high resolution data, so that we cannot use the classification model and then it's a wire, so that we also cannot use a segmentation model as well. So we need a classification, but we cannot resize a lot. So that's why we apply the patch classification, and then we can reach higher up to 98% of the accuracy compared to the normal classification, which is 66% of the accuracy. So this is another one example of the patch classification. So I just introduced 3 things: a GAN model to create some artificial defects, an anomaly model to solve some problem with the class imbalance, data imbalance, and lastly, patch classification to deal with the high resolution data to apply the deep learning. And then all these techniques are included in our auto deep learning vision software. We have a training software called NeuroT. This is like the T stands for the training, so that NeuroT is covering from the data acquisition to the model creation. And then once you create your model, you can apply our model with a runtime library, which is called NeuroR. The biggest benefit of these things is actually we have an auto deep learning algorithm, which optimize deep learning architectures and hyperparameters automatically, so that if you're not a deep learning expert, you can easily create the best performing deep learning model with just one click. So when we train the model, we're going to optimize our model based on your training data, and all your deep learning architectures and hyperparameters will be optimized automatically. And besides auto deep learning, we have many good cases, many good features, as I explained today: GAN model, patch classification, and anomaly classification, and anomaly segmentation. So these are the kind of the new technology we show to this exhibition today. So if you want to see more details, please visit our booth at Hall 8 and 8B11. It's right in front of the entrance of the Hall 8, right over there. Thank you very much for my presentation. Thank you.
Yes, hello everybody. I will give you a short presentation about synthetic data generation for AI-based automation and quality in the field of quality inspection, but also in the field of object detection. You can use this simulated data. So we will have a short look first why should we generate synthetic data? Why do we need it? For AI-based problems or machine vision tasks like object detection or object classification and also quality control, you need problem-specific data sets. And this is always the problem. you need large data sets and you need them problem-specific. So it's not helpful if you have a lot of pictures of cats and dogs if you want to detect defects on metal parts, for example. Yes. So you need special data sets, and typically for supervised learning you have to create annotated data, and this is a very time-consuming and manual process, especially if you are not talking only about pictures but also about 3D data sets. If you have to do 3D annotations, it's much more time-consuming and a tedious process. So, and of course, challenges are always the data sets are not balanced. So you have maybe a few pictures from defect number 1, but a lot of pictures from defect number 2. So it is not balanced, and in the end your AI model will not work well. And if the annotations are done by people, yes, you have of course the influence of the person who does the annotation. You end up maybe with different kind of annotations. You see it here in our logo. You can do the annotation this way, very close to what you want to detect, but you can also put boxes, larger boxes around the complete logo maybe, and this makes a difference in the end for the AI model. So to overcome these challenges, an approach we use is we simulate training data, yes? And we do this based on virtual 3D scenes. This means we have our objects in the 3D scene, we have its material, we have the camera system, the lighting, and of course the defects on the object. All this is built up in a virtual 3D scene. And then we use physically correct rendering techniques to simulate, and we simulate a light flow from the illumination through the scene to the camera. And what are the advantages here? Of course, we can generate a large amount of data and with minimal manual interaction. Yes, it's more or less an automated process. We can model different types of defects in the necessary numbers, yes? So we get balanced data sets. And we have automatically the detailed annotations. They are delivered for free because we know where the defect is, we put it in, yes? And of course there are not only advantages but also challenges. And of course it is a challenge to do these simulation so that it is close to reality, and we have a very small domain gap, yes? And yes, and of course some real data is still needed. In most cases we end up with a combination of simulated data and real data to receive the best results for an AI-based solution. Yes, so what can we do? First of all, I want to show you a bit on these packages what can be done in the simulation is also a deformation. If the object is it's not stiff, we can model also deformations with this cage deformation, for example. Yes, we transfer the object in different positions and end up then with a variety of deformations, and we can also simulate the objects falling on a conveyor belt or falling on a table for later on object detection. What you see here is complete simulated data. It's not real data, it's simulated data shown here in the picture and random arranged, and you see also reflections, you see the printing and everything. Yes? So we are able to create a lot of different kind of situations with the random objects and train our AI model for the object detection. Of course, illumination is important, yes. And we have on the one hand, of course, the illumination in our visual inspection system, but on the other hand, maybe illumination from the surroundings, from our environment, where our vision system will be set up then. And here you see different kind of environmental situations which have an effect on our objects. You see here on top an industrial illumination scene, maybe with cool light, yes, and you see the simulated image in this scene. Here we have an outdoor scene where you see also the leaves of the trees which are reflected on the objects. Or we have a very warm environmental situation with warm light, which is also then shown on the images. As I'm afraid a bit on the screen, it's not so optimal as on the computer. But I hope you can see the differences, yes. And we can also put this in our simulation using environmental maps, yes. Then, of course, what is very important is the material of the object. Depending which kind of material you have, complete other surface structure, you have other reflections, things like that. And we start with only the geometry and a basic material, for example, a metal, yes. And then we do the shading, we modify the surface structure with different kind of maps, diffusion maps, normal maps, roughness maps, to get the final object surface. And of course, we can vary this surface with our shader by putting noise textures on it, low frequency noise, high frequency noise, and combine them also to a resulting noise structure to get different kind of appearance of our object. And of course the defects, this is the reason why we want to simulate, we want to have enough defect images. And for example, we have scratches here on these washers. These are metal parts, yes, and we can simulate scratches by using these displacement maps. We put there automated scratches in this UV map and put it on our object. So we have different kind of random scratches with different length, different appearance on different positions on our washer. And there are, of course, more defects like dents or notches. And here we can use also 3D operations like Boolean operations to put here those notches or dents in the object. Yes. And here you see now a comparison between the real camera images in the upper row and the simulated images, synthetic images from our synthetic data set. And you see there is not a lot of difference you can see. If I hadn't put maybe what is the camera image and what is the synthetic, it would be quite hard to say which one is which one. But you see also, if you look on the upper row, you have a great variance already in the real images. And of course, you need to have all these variants, of course, also in the synthetic data. Otherwise, it won't work in the end. Yes, you see the washers sometimes look quite light and sometimes quite dark with more structure or less structure on the surface. So all what is possible in reality should we also have in the synthetic data. Yes, then we used this synthetic data and trained our neural network. In this case, we used an efficient DET architecture. And yes, to have these 4 classes of defects which we want to detect in our data set. And then we did the training. We did 3 different experiments. On the one hand, we did a training only with real data. Then we did a training only with synthetic data. And then we did a training with mixed data set. Yes, and compared the results. So in the real data set, there was only yes, not a lot of images. We had 40 real images for each defect category. In the synthetic data, we had 500 for each defect category. And in the mixed data, we had these 500 synthetic plus the 40 real images. Okay, how did we evaluate the results? We used the intersection over union here. And of course, true positive was if the intersection over union was larger than 0.5. The false positives, the false negatives, you see here. And we calculated precision and recall. So just for visualization, we see here test images with the predictions. The color of the box represents the defect category. So we have 4 different colors for the 4 kind of defects. We have dents, we have bumps, we have notches, and in the right image we have the scratch. Yes. So, and here is the result. So you see, of course, with real data, we get quite good results already, yes. But, for example, especially the class scratch, the recall is not very good, yes. It is only 0.54. With the synthetic data, we receive nearly the same results, but especially for the scratches, we are much better, yes. Because we had a larger variety of scratches in our training data. And with the mixed data, there we received the best results, of course. But you see already with synthetic data, we received very good performance of our AI-based solution. And in the end, one more example from the object detection. So here you see syringes. On the left side, this is a synthetic image of syringes. So we modeled the syringe from two parts. These are transparent objects, yes. So it's not that easy, of course, but you see the transparency in the synthetic image is quite good, and it looks very realistic. And in the background, of course, we have always the 3D model, so we know exactly the position and the geometry of our objects in this image. And on the right hand, you see then the detections in a real camera image from an AI-based object detection, which was only trained on synthetic data again. Yes. So we used the left box situations for the training and received then very good results from the object detection in the real data set. Okay, so just to give you an overview about our work, if you want to see it more in detail or see this application live, you can come to our booth in Hall 10, booth G45. Yes. So thank you very much.
Thank you very